Okay, for this video I'll be going through general properties of waves, success criteria G. Describe the longitudinal nature of sound wave. So sound wave is actually longitudinal in terms of the processes of compression and rarefaction. So this is the first time we are seeing these two terms. Okay, like all longitudinal waves, sound waves propagate or move as a series of compression and rarefaction. Okay, so once you see sound wave, you got to use these two terms, compression and rarefaction. Now, what are compression? Compression is a region where the air particles are closer together. So let's say the sound wave is traveling in the medium of air. So the air particles are closer together. That is the region where we call compression. And therefore, it will result in an air pressure that is higher than normal atmospheric pressure. Whereas for rarefaction, it is a region where the air particles are further apart, okay, resulting in an air pressure lower than normal atmospheric pressure. So if we look at the diagram below, so for diagram 1, the layers of air are in undisturbed position, right? Because you need vibration, okay, for waves to happen. So once we hit the prongs, okay, or the tuning fork, the prongs will push outward and a region of compression is produced, right? So it will push this layer of air to be closer together. So if they are closer together, it results in air pressure higher than normal. So this is a region of compression. But when this air, the first air layer pushes against the second air layer, it will be pushed back, right? So they will be further apart. So then it creates a region of rarefaction where the air pressure is lower, okay? But this pushing goes continue, right? So in the end, it results in a series of compression and rarefaction. Okay, so the last diagram actually shows a series of compression where the air particles are very close together and a series of rarefaction. Okay, so the air particles here are further apart. So like a transverse wave, we also have a graph. Okay, so the first graph for sound wave is the pressure distance. Why pressure? Because just now we talked about compression. Air particles are closer together, so the pressure is higher. So if let's say now I have a loudspeaker and it causes the air around it to vibrate. So this will actually be compression because the particles are close together. This will be rarefaction. So we have a series of compression and rarefaction as the sound wave is passing through. So if we were to map directly, the air pressure here will be high, okay? For rarefaction, the air pressure will actually be lower, right? And this center line is when there is no sound passing through, no sound wave moving through. So we take it that it is normal atmospheric pressure. So for compression, the air pressure is actually higher, right? So we have a series of compression. We also have a series of rarefaction alternating, right? So what can we get from a pressure distance graph? Pressure is the y-axis. Therefore, it can actually tell us the amplitude. Okay, so it can actually tell us the maximum pressure change. Okay, then this the next thing is we look at the x-axis, which is distance. So we learn in transverse wave that crest to crest is actually the horizontal distance is the wavelength. Similarly, we can apply it here and then we can get our wavelength. So basically, what can we get from pressure distance graph? From the y-axis, which is pressure, we can get the change in pressure. Okay, so it sorts of tells us the amplitude of the sound wave, right? Then the next thing that we can get is from the x-axis. The x-axis is actually distance. Okay, so we can actually get the wavelength. Now, the next graph that we need to go through is displacement distance, which we sort of covered in the transverse wave. Okay, so let me explain the diagrams here. The dots will actually represent, the red dots actually represent, let's say, the air particle. Okay, and the blue line would actually means is the original position of the air particle. So you see all the air particles are spaced equally apart. That means there is no sound wave passing through. But when a sound wave is passing through, it will result in a series of compression and rarefaction, because the sound will push the air particles right in the direction of the wave, of the sound wave. So we see that, but to do this, we actually need to label. So we can call this 1, 2, 3, 4, 5, then 8, 9, 10, 11, 12, 13, 14, 15, 16, right? We map each air particle. So this will also be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so if we were to map each air particle to the next diagram, we can see that particle 4 didn't move, right? It is still staying in its original position. Then we look at the left and right of particle 4, which is particle 3 and 5. Particle 3 is moving towards particle 4. Particle 5 is moving to the left towards particle 4. Therefore, particle 4 is having particles coming close to him, which means it is a compression, right? Similarly, if we look at particle 16, we see that particle 16 did not move. It is still in its original position. And we look at the left of particle 16, which is particle 15, it is moving towards him. So we can also assume that particle 16 is the center of a compression, right? Remember, compression is where the particles are closer together. Now let's look at particle 10. Okay, particle 10 is also not moving, but if we were to look at its neighbor in on the left and right of it, we see that they are moving away from him, and that makes particle 10 a center of rarefaction. Now, because particle 4, 10, and 16, they did not move, so basically their displacement is 0, because we are doing a displacement distance graph. Okay, a displacement distance graph. So if we look at particle 1, 2, and 3, they have actually moved from their original position, and we can actually see that particle 1 moved the maximum. It went from original right up to here, right? So particle 1 is actually having a maximum displacement. Okay, a maximum displacement. So we map it over here. This is particle 1. And for particle 2, it moved slightly lesser, right? So this is for particle 2, particle 1. Particle 3 moved even lesser. So this is particle 3. And this is our particle 4. So if we were to map them, okay, to their displacement, and because displacement is a vector quantity, right, it has magnitude and direction. So if we look at particle 5 and particle 3, they seem to move the same amount of distance, but their direction is opposite. So if we take going to the right as positive, right, so particle 1, 2, and 3 will have positive displacement, whereas for particle 5, 6, and 7, they have negative displacement. Okay, and you can take note that particle 7 actually move the most in the negative direction. So actually it has the largest displacement in the negative direction. So if we were to map every of this particle in terms of its displacement, we can then draw out this displacement distance graph, right? And we learn from transverse wave that for a complete wave, we are looking at the x-axis distance. So this will actually gives us the wavelength. Okay, but we started off from particle 4 and we ended up at particle 16. Both particle 4 and 16 are compression. So can I say that from compression to the next compression is equal to wavelength? Okay, so this is what you can get from a displacement distance graph, similarly to the displacement distance graph for transverse wave. Okay, so now we do a quick comparison between displacement distance and pressure distance graph. So if we start with displacement distance, we can actually get from the y-axis, right? The y-axis we can get amplitude, and from the x-axis we can actually get wavelength. Okay, so for pressure distance graph, remember at the peak is actually a compression, but at the compression the displacement is actually 0. For rarefaction, okay, which is maximum negative displacement, we have lowest pressure, right? The displacement is also 0. Okay, so this is the comparison. So we have another compression here. This is the compression, right? Next, the last graph is our displacement time graph. Okay, so recall from transverse wave dt graph, the y-axis we can actually get amplitude. The x-axis we can actually get period. Now, is this the same for our longitudinal wave? Okay, let's take a look at how one particle behave, because displacement time graph is actually a video of how one particle move during a full oscillation. So at time equals to 0, the particle is in its original undisturbed position. And let's say now the wave is going from left to right. So in one step or 1/4 of a period, it will move one step. Okay, so once it has reached the maximum displacement, it will then move back, okay, using another step, which is half a period, right? So that's why we have t/2. But it will not stop there. It will continue moving towards the left so as to complete one oscillation. So it will now take the third step to the other extreme position. Okay, and that is 3/4 of a period. And finally, to complete the full oscillation, it has to go back to its original, right? So this will be step 4. So now if we were to link up the particle's position, we will actually get something like a transverse looking wave, right? This is what you are very familiar with. And we can then translate it to our displacement time. So similarly, the y-axis can actually tell us the amplitude, right? The x-axis, right, which is the time taken to complete one complete wave, that will give us the period. Okay? So if we have the period using our t equals to 1/f, we can then get our frequency. Okay? So you can read through the notes here by yourself. Okay, let's try G1. Okay, G1, the graph shows at one instant the pressure variation along a sound wave. Now let us take note, it is a pressure distance graph. And what can we get from a PD graph? The y-axis, okay, which is the pressure, can tell us the change in pressure, right? So if we have a louder sound with higher energy, this value is going to be higher. Okay, the amplitude that the change in pressure will be higher. Now, how about the x-axis? X-axis is distance. Okay, so distance will then gives us the wavelength. Okay, so if I were to draw this, this will be one. The horizontal distance will be the wavelength. So wavelength will be x. Okay. The rarefaction, where will it be? Now, rarefaction is where it will be lower pressure than atmospheric pressure. Okay, so it will definitely have to be at Q. So this position will be the crest. So answer is C. Okay, G2, a sound wave travels through air as a series of compression and rarefaction. Okay, which rho compares the air pressure in a compression and a rarefaction to atmospheric pressure? Air pressure in compression must be higher. Air pressure in rarefaction must be lower. So answer is B. Very simple. Okay, so that's all for success criteria G.